All right, in this lesson, we start talking about wave characteristics. This video is mainly going to be talking about intensity and how it relates to amplitude and radius away from a source. First things first, there are two ways of describing these waves, or there's also sort of two ways of drawing them. You can draw them as wave fronts, and you can draw them as rays. A ray is sort of exactly what it sounds like. You can picture these arrows coming at you, and it is the direction that the energy is traveling. So that's how we would draw rays. Wave fronts, however, is almost like saying that these are perpendicular to the direction of energy traveling or energy transfer. So almost if you imagine a wave coming at you, you could think about the wave front being perpendicular to the direction they're traveling. So I could draw these in as wave fronts, which we often see, but you could also sort of draw them as energy, in which it's more like drawing arrows coming at you. So wave fronts, rays. Okay, this is sort of an example of wave fronts coming at you. If you imagine a light source in the middle here, maybe you have a light source in the middle and it is emitting light waves, we would call these wave fronts. Rays, however, highlighted here in red, are the direction of travel of energy. So energy would be emitted in all directions, and we can draw rays like so. Wave intensity. This is defined as the amount of energy per unit time flowing through an area. Now that sounds complicated, but it's not that bad actually, because we already know what this means. Energy per unit time. Energy per unit time is something that we are already quite familiar with. Energy per unit time, that is a watt. So we're actually going to be using sort of the unit of power. Energy per unit time is power. So it's basically like saying power per area. That leaves us with this sort of these units down here. Power per area. The standard unit would be watts per meter squared. You could also write this as a fraction. Watts per meter squared. Let's talk about wave intensity. This section is very intuitive, and this is a great photo because if you look down, you can almost see the shadows created by the frame of the window. What's happening here? You could almost imagine either the wave fronts or the rays coming at you. And almost you can see that this angle causes it to almost become more spread out. That's a very important concept. And we have some good images coming up thanks to Cognitive Intelligent Textbooks, which is a great resource if your school can approve it. Let's look at this here. Let's look at the intensity away from a light source. So if I have some light source in the middle here, right, this would be happening in all directions because it would be giving out a spherical, it would just be a spherical light shining from in all directions. Shining in all directions. Think about it. There is some amount of energy, or we could say power, right? Power would just be energy per time. But as the waves get further, as the light is emitted, and you can clearly see that it's got to be the same amount of power, but spread out over a larger area. So what started out as think about this. Think about all the energy being concentrated into this one sheet. But by the time I make it to this sheet, you can clearly see that the area has sort of caused the power or the energy to spread out. It's like dispersing the energy. So here as well, you can see that the area is increasing. It's not a coincidence that as you back up away from a light bulb, the light gets more faint, right? The light source is further away, so it's losing its intensity. And we can actually say that intensity is inversely proportional to the radius squared. That sounds complicated, but it makes a lot of sense in just 1 second here. So this is my radius. You could also think about it as distance. As I increase distance, you can see that the intensity is sort of dissipating. It's sort of fading away. When I double my radius, look at the area. Doubling my radius actually quadruples the area. Interesting. So it's quadrupling, sort of, it's diluting. It's quadrupling. If I go to triple my radius, this compared to this initial radius, so I have now triple the radius, you can see that the area that was, or the power that was in this one sheet is now, it's actually 9 times bigger. So there's a relationship going on here, and it's very simple. Think about each one of these sheets as being part of this sphere created, a light source sphere. There's actually a quick way we can compare this or use the surface area of a sphere to explain this. This is given to you in the data booklet, this relationship, and it doesn't use R, although most people prefer to use inversely proportional to the radius squared. We're going to look at this equation now, and it makes perfect sense. Look at the sphere. This is the surface area of a sphere. So it actually makes perfect sense where this equation comes from. The intensity of a light source, is equal to power divided by area. That's it. Intensity is power in watts divided by area in meters squared. The only thing that makes this equation look a little bit intimidating is it's like, whoa, where did the 4 pi r squared come from? That is simply the area of a sphere. Because think about this. These sheets are in a spherical shape. So the area that the power is passing through is simply, or the energy is passing through rather, this surface area would be the surface area of a spherical shape. Okay, let's check this one out. We're talking about the intensity compared to the distance. And the distance, if we're talking about light emitting, energy in all directions, we can also call this radius. In the IB course, it is given to you as inversely proportional to radius squared. That is just like saying 1 over x squared or 1 over r squared. I prefer to use r, but it is totally up to you. So I'm going to write it as radius. That is just my personal preference. All right, so it's inversely proportional to the radius squared. This problem becomes not very difficult. I know the intensity of a light source, okay, 6 watts per meter squared. That is what the intensity is at a distance 12 meters away from the light source. What if you back up? What if you back up to be 36 meters away from the same source? Well, based on this relationship, that they are inversely proportionate to the square, that means that as my radius increases, my intensity will decrease. Well, let's just look here. My radius has actually tripled. So we could almost say that my new radius is equal to my old radius times 3. It's tripled. So I can actually, you just use this mathematically, and it's pretty simple. I have tripled my radius, and I keep this statement true. If I've tripled my radius, this is going to give me, if I expand this exponent in here, now I could almost say that it will be 1/9 of the intensity. But at 12, my intensity was 6 watts per meter squared. At the 36 meter distance or radius away, I'm going to have only 1/9 of that intensity, which will give me 6/9 or 2/3. You could also do that as a decimal, up to you. But this will be my new intensity at that spot. So you can see how being inversely proportional to the square means that it decreases very quickly, right? This distance was tripled, but you can see that I've gone from 6 to less than 1 watt per meter squared. Intensity and amplitude. Now this is also something we can talk about using the proportionality, and it is basically that intensity and amplitude, now they're actually proportional, but the intensity is proportional to the amplitude squared. Okay, this is funny to think about, but you can think about surfers. They kind of know this because every surfer knows that when you go from a 1 meter wave to a 2 meter wave, it doesn't just double the intensity. Doubling the wave's height does not just double the wave's intensity. It actually feels way more than twice as intense, okay? So you'll see what I mean in a second there. We can basically say that if I have some intensity, like in the last one, I had 6 watts per meter squared. If I were to, for some reason, double the amplitude or have the amplitude doubled, okay, if the amplitude is doubled, then I will end up with an intensity that is 4 times. Okay, so it is important that you know how to use these sort of proportionalities, but it's pretty straightforward when you sub in the value. So my A value in this case is actually now double the amplitude. So when I sub that in, I get that value. I'll show that one more time. Okay, if I let A be doubled, so I'm letting A equal double A, okay, sub that in. It's almost like I'm saying that the intensity is doubled, but it's doubled times 2. So it's squared, 2 squared. I'm going to have the intensity increase by a factor of 4. Okay? So this intensity would actually shoot up to 24 watts per meter squared. So doubling amplitude actually quadruples intensity. Okay, this is one that we can do together because it's pretty complicated. A transverse wave of amplitude A and frequency F gives an intensity of I at a distance x from the source. That sounds really complicated, but it's going to be summed up pretty quickly here. By what factor does the intensity change if the amplitude is doubled and the distance to the source is halved? That is not easy. If the distance to the source is halved, I'm actually moving it closer. So that means that the intensity should go up. If the amplitude is doubled, the intensity should also go up. Let's remember these two relationships here. I am doubling the amplitude, but I'm halving the distance. Remember, you can use x or r in this case. Okay, well, we just did the one where we double my amplitude. Because it's proportional to the square of the amplitude, we actually just saw this a moment ago. I'm actually going to increase the intensity by a factor of 4. But what happens when I halve the distance? Well, if I halve the distance, it's like saying 1 over a half squared. That will actually simplify to a big ol' 4. Take the time to pause and make sure that you understand that. That will basically give me 1 divided by a quarter, which is like saying multiplying by 4. Okay? It's like dividing by 0.25. Dividing by 0.25 is like multiplying by 4. Okay, so if moving closer or halving the distance is actually going to quadruple, okay, and doubling the amplitude is actually going to quadruple, my new wave will have 16 times the intensity. So I'll take my old intensity and multiply it by 16. That is pretty incredible. You can pause the video and look at this explanation as well if you'd rather see the formal explanation. This is not my material. This is from Cognity Intelligent textbooks. Give this one a try on your own now. The answer is not a whole number, but it is pretty close to 1. This one I'll leave up to you. Pause the video